Okay, so maybe we can get started. So yeah, thanks to Yuxun's invitation. Today we're going to have Dr. Ray Zhang to be our speaker for the seminar. And Dr. Ray Zhang obtained his PhD degree from the University of Maryland in 2023. And he's currently a postdoctoral researcher at the Physics Division of Argonne National Lab. His research interests focus on hadron structure, especially the Parton distribution or Parton physics from Lattice QCD. So today here he's going to give us a talk about resumming large logarithms in the lattice calculation of generalized Parton distributions and distributions, alternative Meson distribution and QCD. I'm not sure why you can adjust. Ray, probably you can start now.
Okay, thank you. Thanks, Bigeng, and thanks for all the hosts for the invitation. It's a great honor for me to join this seminar. Today, I'm going to present our recent work on the resummation of large logarithms in the lattice calculation of Parton observables, like the general Parton distribution and the Meson distribution amplitudes. So in this, in this talk, I will. This is the outline of my talk. I will first briefly introduce the Parton observables relevant to the QCD exclusive processes, and then I will describe how these observables are calculated from the lattice. And I will go into how we deal with the large logarithms in the perturbative matching of these observables to improve the precision of our calculation. And then I will show the results for applying the method to the calculation of Meson distribution amplitudes and the generalized Parton distributions. We know that the factorization is actually a foundation of studying hadronic physics on the colliders. That relies on all the observables could be factorized into the ultraviolet physics and the infrared physics, plus some corrections, power corrections. So for the ultraviolet part, we are able to calculate them in perturbation theory due to the asymptotic freedom. And this part are usually called the hard kernel. And for the infrared part, we don't really have a good way to calculate directly, but we know that there are some universal parameters that are the same in different processes for the same kind of physics process. So these universal parameters are extremely helpful if we could know them exactly, and we are able to use them to make prediction for future experiments. Here, there are two main classes of these processes, and they depend on different universal Parton observables. The first kind is all that we know much earlier is the inclusive process. It's like the deep inelastic scattering. So we sum over the final states. In this case, we care about the total cross section, and that's where the factorization happens. And the relevant non-perturbative observable is called the Parton distribution functions. So, and as shown here, it's like an electron scatter off the proton and break it into pieces. There's also another type of processes proposed like 30 years later. It's like the exclusive processes where we identify all the final states. So of course, it's much more difficult to realize on collider physics. And in these processes, the factorization happens at amplitude level. And the relevant processes are the deeply virtual Compton scattering and the deeply virtual Meson production, and the recently proposed single diffractive hard exclusive processes. So in these processes, the most relevant Parton observable is the generalized Parton distribution. And in those processes with Meson production in the final state, the Meson distribution amplitudes also enters the factorization. So the generalized Parton distribution is a very important quantity, as you see from the four goals of the EIC physics. We find that the two of the four goals are directly related to GPDs. They are the three-dimensional structure of the proton and nuclei, and also the understanding the proton spin. So why are GPD related to them? So first, from its definition, we know that GPD is depending on multiple variables. It's not only the longitudinal momentum fraction x that the parton carries with respect to the hadron, but also a momentum transfer, like the delta here for the initial between the initial and the final state hadron, and the psi here called the skewness, depending on the z component of the momentum transfer uh, divided by the total the momentum of the hadron. So in this decomposition, if we take a Fourier transformation of the prime of the momentum transfer delta, we will find a spatial distribution in the transverse plane. So that gives us three-dimensional imaging of the partons inside the nucleon, as shown here. Also, the GPDs are directly connected to some important properties of the hadrons, like the gravitational form factor. If we decompose the energy momentum tensor into different Lorentz structures, we find that these gravitational form factors are directly related to the first moment of GPDs, except for the C bar, which is more complicated to understand. Also, the GPD moment is related to the spin of quark and gluon contributions inside the hadron. From this some rule of the proton spin, we find that the quark and gluon contribution to the proton spin can each be obtained by the moments of GPDs. So the GPD is a very important quantity for us to understand, but its extraction from experimental data are highly non-trivial. So so far, we have most of the knowledge about the PDFs because we generate a lot of data from hadron colliders and also the electron proton colliders, and especially in this process, in this DRS process, the leading order contribution comes from a convolution of delta function convoluted with the PDF, which pins down the PDF at the momentum fraction of Bigeng x. So as long as we have this large set of DRS data, we can get enough information about the X dependence of the PDFs. On the right-hand side, I'm showing the parameter space of PDF global analysis. As you can see, the data range goes from 10 to the minus 4 in momentum fraction up to order 1 and covers a very large range of Q square. So far, the global fitting groups can determine a very precise quark and gluon PDF inside the nucleon. On the other hand, for the GPDs, things become much more complicated. there are several difficulties to extract the full GPD from experimental data. So first challenge is that GPD has multiple dimensions. It not only depends on the longitudinal momentum fraction, but also on the skewness and the momentum transfer. So in order to get the same precision of determination, we need to have a much more experimental data to do that. Second challenge is that the most important process to extract GPD is the deep virtual competence gathering. But this process is actually a subleading process in the experiments. There is a contamination from the beta Helter process, which is just the photon scatter off which is just the photon emitted from the electron, and this virtual photon is not really probing the inner structure of the proton. So we need to get rid of this contamination first. The third challenge is that since this factorization happens at amplitude level, it is always a convolution with some hard kernel that integrated over the full X region. This is an example of the DVCS. You see there's a hard kernel of 1 over X minus cosine. So it is not like the delta function in DIS that helps you get to the specific X, but it's always an integral. So this process is mostly sensitive to the region that's X close to cosine. And the recently proposed single diffractive HEP has a wider, but it is still limited sensitivity when you tune the parameters. So when solving this inverse problem to extract the GPD from experimental data, there's another issue. There's an issue called the shadow GPDs, because you can, in principle, have degenerate solutions to produce exactly the same experimental data. Like this shadow GPDs, when convoluted with the hard kernel, just give you 0 contribution. So you will obtain exactly equal feeds, like shown on the right-hand side, and you could not distinguish which one is better. There are similar issues for the pion distribution amplitude, which also enters into the exclusive processes. It is the probability amplitude of pion in its minimal Fock state of a quark and antiquark pair, which carries a momentum fraction. So the pion DA is usually determined or detected through the form factors, but it enters into those exclusive processes for determining the GPDs. Extraction of pion, of course, since it's the factorization of at the amplitude level, it has a similar issue that you need to integrate over the full X region, and you cannot really get the local X dependence very precisely. So we really need some information from first principle calculation. Perhaps if it could help us to get some information of the local X dependence. On the left-hand side, you can see that this is the parameter space of GPD for cosine and X. And the experimental data mostly lies on these lines of X equal to plus minus cosine as the red band. But in principle, lattice QCD could help us obtain information in these white regions. So with the input of lattice QCD, we are promising to get a much larger range, to cover a much larger range of the parameter space and have a better determination of GPDs. On the right-hand side, we can see example by Yuxun and his collaborators to extract GPD through universal moment parameterization. So by taking the lattice data into their feed, they found that they can get a much more stable fit from their strategy. And they just take the lattice input for several X dependencies. So the lattice QCD calculation of GPD really helps us to understand GPDs as a complementary knowledge to the experiments. And then how do we calculate them on lattice? So the basic idea of lattice QCD calculation is to reformulate the path integral into statistical physics partition functions. Simply by a weak rotation, we find that the phase in the path integral is converted to something like a weight factor. And this weight factor is positive and bounded, which is perfect for a Monte Carlo resampling. Then we can measure the expectation value of at the observable through just a statistical average over some randomly distributed gauge ensembles, and we can simulate those on large computers. But to do that, of course, to do it numerically, of course, we need the discretization. So basically, we discretize the four-dimensional space-time and put the quark and gluon fields on these gauge ensembles. After that, we can construct the correlation functions to extract physical information from it. These are examples of the two-point correlation function that basically mimics a hadron propagating in time from 0 to some Euclidean time t. And if we insert some current, then we got a three-point correlation function. So in our calculation, we basically obtain the distribution amplitude from the two-point correlation functions and the three-point, and we obtain the GPD by measuring these three-point correlation functions. Then after obtaining these correlation functions, since these lattice interpolators are not representing a single hadron state, it represents a combination of all possible hadron states or some multi-particle state with the same quantum number. So what we really want is to extract the ground state matrix elements. Then we need to go to large enough Euclidean time that all the excited states with heavier energy or heavier mass just decays out. Then we can extract the ground state matrix element. So one greatest success of lattice QCD is the prediction of hadron spectroscopy with just a few inputs of the pion kaon mass and the sigma mass. And the Xi mass in the baryon sector. So with these few inputs, lattice QCD is able to make a very precise prediction of the heavier meson states and baryon states. Some of them are even more precise than experimental measurements. This demonstrates that lattice QCD is indeed a powerful non-perturbative tool to calculate the QCD observables from first principle. But when we try to move on to calculate the Parton physics, we got some problem because all the Parton observables are defined in the framework of hadrons on the light cone. So all of them are defined as light cone correlation functions. But when we weak rotate the Minkowski spacetime into Euclidean lattice, we just got 0 over here. So these correlation functions are in principle not directly calculable. And people have developed different methods to extract partial information of the Parton physics. the most traditional way is the calculation of the moments of Parton distributions through OPE, where we can just calculate local operators on the lattice, and that encodes the information of the lowest moment. Like 10 years ago, it was proposed by G to calculate the x dependence of Parton observables through a large momentum expansion. And also, it was followed that this information, the information of Parton physics can also be obtained by a short distance factorization from similar correlation functions. In this work, I will most focus on the large momentum expansion approach, which give us direct information of the x dependence. So the basic idea of large momentum effective theory is that we measure a correlation function in the Euclidean space, but it is inserted in a hadron state that's boosted to a very large momentum. Then we can do a large momentum expansion, and in the leading order, it corresponds to an infinite momentum limit. And that limit can be related to the light cone distribution through a perturbative matching. Of course, we will then get some power corrections in this expansion, but they are suppressed by the large momentum. So as long as we go to higher momentum, we can get more precise determination of the Parton physics. Note that in principle, we cannot get close enough to the endpoint regions because in that region, the power expansion breaks down. In the calculation of LaMET, there are several systematics we need to understand. We need to address carefully to get a precise determination and also accurate determination of the Parton observable. So the first systematics is about the numerical part, is the lattice artifacts. Since we are simulating on a discretized lattice, we do have some discretization effect, and also we have the finite volume effects. And if we measure all these observables at non-physical pi mass to reduce the cost, we got some extra systematic error from the Carroll extrapolation. So these are the lattice artifacts, and it has been addressed more and more by it has been addressed improvingly addressed by putting more and more computational resources into it. Also, there are some unknown power corrections. That's the nature of this large PZ expansion, that we don't really know what these power corrections are. So in order to reduce these effects, we have to push to large momentum. There are some theoretical systematics that we could, in principle, handle, and we could, in principle, reduce them to a very small level to not affect our calculation. And in the recent years, there have been three important systematics addressed. One is about the realization of the lattice measurements. And this is like eventually we have kind of agreed that to use the hybrid realization scheme, which has a perturbative matching to MS bar, that where the factorization is proven. Another systematics is about the power correction, but here it's as a linear order. So this correction should not appear in the factorization, but it appears because we have some linear renormal in our realization and also in our perturbative matching kernel. This systematics has been addressed by the linear renormal resummation that carefully regulates the Reloman effect and cancel between the renormalization and the matching kernel. So we can get rid of the linear power correction and reach the quadratic power accuracy. And a last class of systematics is about higher order corrections. Of course, we know that higher order corrections could be important in some processes or in some regions. So we really need to get a higher order perturbative calculation of the matching kernel. Also, there are logarithms in the perturbative matching that depends on the factorization scale and the renormalization scale mu, and also some physical scales. So when the factorization scale or renormalization scale mu is very different from your physical scale, in principle, this logarithm can be large, and at higher order, they are still non-negligible. So in this talk, I will focus on this last systematics about the large logarithm resummation. In this slide, I'm showing the recent progress in the precision control of LaMET PDF calculations. Like in 2022, it was the first implementation of the two-loop matching on a pion PDF calculation. And later, we start to study the renormalization group resummation of the Dirac logarithms in this calculation. And we find that the perturbative calculation, it really breaks down below 0.2 in X at this momentum. So this indicates that the LaMET calculation cannot really tell us what your X dependence below 0.2 at 2 GeV. Also, we developed the linear Reloman resummation to remove the linear power correction and get a better convergence in perturbation theory. And very recently, it was developed that to resum the threshold logarithms in the LaMET, that when X goes close to 1, the cancellation of soft divergence is not complete. That results in a very large logarithm and needs to be resolved. And this numerical result is still in progress. So that's just the progress in PDF. Can we just generalize all these techniques to the calculation of DA and GPDs? Well, we found that some of them can be easily generalized, but some of them can't. So we can classify these systematics into two different parts. There are some state-independent systematics, like the renormalization is just the operator level, and the linear Reloman resummation, because the linear Reloman are the same in the Wilson line, is regardless of the operator structure or the external state. And the threshold resummation is also state independent because when we factorize the matching kernel in the threshold limit, again the state dependence disappear there. So all these three are straightforward to generalize to DA and GPDs. However, the renormalization group resummation turns out to be highly non-trivial for these two of the so-called off-forward matrix elements, because they have different momentum in the initial and the final state, and different momentum for the incoming and outgoing partons. And that's what I'm going to address in the next section. So the resummation of logarithm in quasi-PDF is kind of straightforward because we have the Dirac evolution equation. This also corresponds to the zero skewness case of quasi-GPD. In this case, in this limit, the matching of quasi-GPD is exactly the same as the matching of quasi-PDF. We can make an analogy to deep inelastic scattering, where the Q there is twice the Bigeng X times P times PZ in the bright frame. So here in quasi-PDF, we have a physical scale of 2xpz depending on the Parton momentum xpz. Then using the DGLAB evolution, we can resum the fixed order matching kernel by evaluating the kernel at the physical scale 2xpz and then evolve to the scale mu using the DGLAB evolution. With this resummation, we find that there's a non-negligible effect for x smaller than 0.4 or 0.3. And we can determine what range we can really calculate with LaMET. So it is also proposed to resum the threshold resummation about this log 1 minus x over y. And that's mostly related to the large x regions. However, if we move on to the off-forward case, we find there are several very different properties. In the forward matrix elements, we have the same initial final state. So there's just one single Parton momentum, xpz, that corresponds to one single scale. That's twice the Parton momentum. So we can solve this resummation with just one evolution equation, the DGLAB evolution. However, when we move on to off-forward matrix elements, like we have a different momentum in the final state, P prime. For dA, this P prime is just a vacuum state, so we can think it as a zero momentum there in perturbative matching, and that corresponds to psi goes to one limit. So in this case, we have two partons that each carries a different momentum, x plus psi or x minus psi times pz. Then they correspond to two distinct physical scales. But we only have one ERBR evolution. So in principle, we cannot resum both logarithms once with this evolution equation. And we need some further equations. This is an example of the mu dependence of GPD in different kinetic regions. In the ERBR region, we have two separate terms. It's a piecewise function. And in the DGLAB region, we have one single term. So to get a resummation, we first need extra evolution equations. And we also need to know what exactly these scales are. If we take a closer look of the GPD matching kernel, we actually found some interesting features. So the GPD perturbative matching can be organized into three parts. Each of them carries a different logarithm. And we are able to identify all these logarithms are, like what the physical meaning of them. Actually, the first logarithm corresponds to a momentum of an outgoing quark or incoming antiquark momentum. And we find, very interestingly, this logarithm becomes large when psi plus x goes to 0, but it has a prefactor, psi plus x. So in principle, when psi plus x goes to 0, this logarithm doesn't contribute. Its limit goes to 0. A similar thing is for the second logarithm for incoming quarks. This is just an observation in the first at one loop order, but we actually have an argument that from these kind of corrections, you always get an x plus minus psi as a prefactor when you generate these logarithms at higher order. So no matter at which order you are, you always get a zero limit when x plus minus psi goes to 0. However, there is an exception because we notice that there is a denominator psi plus y or psi minus y here. And if we go to the limit when x is close to y, this denominator will cancel the prefactor and you still get a very large logarithm. For the gluon, for the third logarithm, we find this to be the gluon emission momentum. that's corresponding to this gluon momentum here. It is also enhanced when x close to y. So because it's log 1 minus x, of course. So we find that in the ERBL region, all the logarithms are important only in the threshold limit when we have a very soft gluon. And in this limit, we can actually do something more. We can further factorize the matching kernel into different pieces. This can be explained by the soft collinear effective theory and match it to QCD. So eventually you will get the pseudocofactor, one representing the quark and one representing the antiquark, or maybe a reverse, depending on the sign of the momentum. And you will get a jet function representing the gluon momentum. And after this factorization, all the three different logarithms now exist in separate pieces. And they actually follow independent evolution equations. This is one loop expression for these functions. And we notice that there are double logarithms appear because in this threshold factorization, we are separating the soft modes. So there will be both soft and collinear divergences appearing in these logarithms. When we combine them together, the double logarithm are canceled between the pseudocofactor and jet function. So since they each evolves individually, we can resum them to get the solutions. But each of them depends on independent in physical scale. With this resum formalism, we can correct our matching, fixed order matching kernel, and also for the inverse matching kernel. Then we need to answer what are these physical scales inside the pseudocofactor and jet function, such that we can get an exact solution to them. We need to determine two scales for the pseudocofactor and one scale for the jet function. The determination of half scales in pseudocofactor is easy because it has a clear meaning of the quark momentum. And then we can identify the two scales as psi plus or minus x times pz. But for the Simon half scale in jet function, naively, we would say, why not choose the gluon momentum, y minus x times pz? Well, if we choose that, since we know our matching is a convolution integrating the variable y, it means that whatever x you have, you will always get some region that y is close enough to x, and your semi-hard scale mu I goes to 0 and hits the lambda pole. So you cannot really calculate it in perturbation theory. So here we follow the strategy proposed by the Becker and collaborators in the threshold resummation of DRS. But so they convolute the jet function with a PDF modeled by a power law near the endpoints. But we find that we don't really need a model. The semi-hard scale is actually related to the elasticity of GPD. So whenever you have a non-smooth point, at that point, GPD is non-analytical, you will generate a new physical scale. So we can eventually argue that the actual Simon-Hart scale choice could be twice the x minus x0 times pz, and this x0 is the closest non-smooth point in your GPD distribution. In real calculation, since we know GPD is not smooth at psi plus minus psi, and it's not smooth at plus minus 1, so we could, in principle, have 4 different Simon-Hart scales, depending on which x we choose. So, however, so that's all story for the ERBL region. We have the initial scales, we have the solution, and we know how to correct the matching kernel. then our resummation is done. However, for the decay operation, we know that this threshold factorization does not simply work because if we go back a step here, when psi goes to 0, these two logarithms are exactly the same logarithm. And combining them together, this 1 over psi enhancement will eventually lead to a cancellation of the prefactor, and you will not get a zero limit when you are away from the threshold limit. So you always get a large logarithm, no matter whether you have x close to y or not. We need a new strategy for the Deagle operation, but we find a way to do that. So if we choose a hard scale first, that corresponds to 2x times pz, then these two logarithms now become not the psi plus x over mu, but is psi plus x over x. And this term will always be finite when x goes to 0 or when psi plus x minus x goes to 0. And then we still have the same argument that only in the threshold limit, this logarithm is important, and we can do the threshold factorization. And that allows us to resum the remaining logarithms in the threshold limit. So we propose a two-step resummation in the Deagle operation that we first evaluate our full matching kernel at this hard scale of 2xpz. Then we can do a threshold factorization and resum the remaining logarithms. And eventually, by combining them together, we need to evolve the matching kernel back to scale mu because we start at a different scale, 2xpz. So that's all our strategy for the large logarithm resummation in GPDs. And in DA, since it just corresponds to the ERBL region of GPD in the psi goes to 1 limit, is the same strategy there. Let's show our results for the calculation. First, for DA, we have some lattice data, and we can apply it to the just real data. So for the DA, we measured on two different ensembles. One is with the Hisk fermion, the other with the domain of fermion. That's a Carroll fermion action. These two ensembles have similar lattice spacing around 0.08 Fermi and physical pion masses, and we boosted the pion to like around 1.8 GeV. We also measured the K-on DA on the Hisk ensemble and boosted to a high momentum. And this is an example demonstrated with the K-on distribution. As we see on the left-hand side, we turned on the resummation of the pseudocode factor and the jet function separately, and we found the resummation effect to be opposite to each other. So there is a cancellation when resumming the pseudocode factor and jet function. That is probably coming from the cancellation of the double logarithm. And on the right-hand side, I'm showing this scale variation in this resummation. We see that in mid-x region, the scale variation is controllable, but when x gets closer to the endpoint, the scale variation starts to diverge, which indicates that the LaMET matching does not work beyond the point. And this is a comparison of our result for the K-on and the pion distribution on the same ensemble, and the pion distribution on different ensembles. So we found that the K-on distribution is more narrow than the pion, and for the with a domain or fermion, we got an even flatter distribution. But the discrepancy is not very large. It's still within 260. For the GPD, we don't have a lattice data to test on right now. So we test on a GPD model. Here, this model is motivated by the double distribution that obeys the polynomiality of GPD moments. So in order to get a better idea of our calculation, we choose a larger momentum here in our matching kernel up to 4 GeV, so we can get closer to the to these singular points, and we can extend out the range of our calculation such that we can do some inverse matching later. So on the left-hand side, I'm showing the result for I'm showing the resummation effect of the GPT matching from light cone GPT to quasi GPT. So you see that the green band and magenta band has some noticeable deviation from fixed order matching when it gets away from 0 and gets closer to plus minus cosine. And there's a scale variation that blows up when it's very close to these points. On the right-hand side, I'm showing the scale variation with two different implementations. They both suggest that we cannot get too close to cosine or too close to 0 and 1, or sorry, to -1 and 1. So eventually we conclude that the scale variation blows up near these points for this large momentum. And what we wanted to do next is to implement an inverse matching on it. However, we don't really know what the quasi GPD is in this region, but we know that in our lattice measurements, these functions are usually continuous, right? So they cannot be too different. So we do an interpolation in these regions. But to allow some variation, because we know in this region there are some artifacts like the power correction or non-perturbative effects. So we try different strategies in the interpolation. We try a sublime interpolation and the linear interpolation. And as you see, they are very different in these regions. So we can kind of think this difference in different interpolation strategy as non-perturbative effect or some power correction effects. But after we implement the inverse matching kernel, we just find that a very good agreement among different strategies. Here I would like to address that the resummed inverse matching kernel is not exactly an inverse of the matching kernel because the resummation of the logarithm terms are different there. When you resum the inverse matching and matching, they are not exactly the same because it depends on what initial scales you are choosing, and they are usually different in the matching and the inverse match. So in principle, you could get very different results by implementing matching then inverse match. But here we still get a very good agreement with the initial GPD model. Okay, thank you. So and this suggests that our method is self-consistent. And it also indicates that the LaMET matching is highly local because our very different interpolation strategies still give us the consistent result. And the power correction or non-perturbative effects near those endpoints or singular points does not spread when we implement the inverse match. So that's all on my talk. So to summarize, we developed a first systematic approach to resum the large logarithms in quasi-GPD matching at the non-zero scales. And we can also apply this matching to quasi-DA by taking cosine goes to 1. Our resum results clearly suggest that the LaMET calculation is reliable when within some region of X, when we stay far away from cosine and plus minus 1. And when we go to larger momentum, we can push this, we can extend this range of calculation. And our results for inverse matching and interpolation are self-consistent and it also shows the high locality of the LaMET match. For the future work, we will try to apply this method to real lattice data of quasi-GPD calculation, and we will try to address more about the Resummation effects in this matching kernel. So that's all of my talk. Thank you.
Any questions?
I have an outsider question. Can you hear me?
Yes, I can hear you.
Okay, thank you. I have this is not my specialty, so this is kind of an outsider question. When you have these different regions, the D glap and the E something something something.
ERB.
Herbal.
Yeah.
Herbal. Okay. Presumably, because you have to some non-perturbative effects differently, there's not like a smooth matching between the regions. That's the first part of my question. Is that correct?
Yeah, it's not smooth. It's not smoothly collecting these regions in our lattice calculation because at fixed order, it's kind of smooth. But if you do resum higher logarithms, you notice that when you get close to these boundaries, you got some physical scales that's very small, which means that you enter some non-perturbative region, and your perturbative calculation cannot be continuous.
So my follow-up question would be, A, is it of interest to attempt to make some like matching kernel that lets you kind of smoothly connect between them? And if so, are there good ideas how to do that? Or you could maybe simultaneously fit both together?
I see. So I think this could be difficult because there is like a hard boundary here. And if we want to get a matching, then you probably want to get some region that both theory would still that both you probably need some overlapping region to match the two. But here, I think the issue is that when we extend both regions to the boundary, the calculation breaks down.
Okay, so maybe I could rephrase the question slightly differently. Maybe not necessarily a smooth matching, but you have the kernel, the non-perturbative function you want to determine, and then times some perturbative stuff, and then maybe you can multiply it by some polynomial error correction or something that allows this kernel to be forced to be the same in two regions, but then there's some ability to like
got it.
Let the different regions separate a little bit, as long as these corrections are somehow small.
So yeah, in principle, you can do some modeling, right? Collecting different regions. In principle, you can always model that. But I think so far our goal is to calculate this without modeling and have a well-controlled systematics. So we want to first identify in which region we can calculate reliably with controlled systematics. And then in between, as I mentioned here, since whatever you interpolate here is not really affecting that much to the other regions. So I would say interpolation may work. Yeah, you can do that to get a smooth kernel connecting all these regions, and you may get the same result, the correct result in these regions, but you still missing knowledge in this near the boundaries. Mm-hmm.
I guess, yeah, I don't really want to model so much as just model some systematic. So that there's still some rigorous something I'm getting at. Yeah, just curious. Thank you.
Yeah, I think it's possible, and you can always do that. And but our goal is not. Yeah, our goal is mainly focusing on calculating them separately, and I think we don't really need a smooth collection among them because you are always calculating one x point each time. You just calculate one single x point. You don't need a full profile function. Thank you.
May I ask a question too? So
Sure.
when you do the resummation, I have two questions. So when you do the resummation for pi distribution amplitude, does this resummation actually will affect your moments, the pi distribution? I remember one of the Argonne Blue-Heaven result also computed the moments, right? Does resummation actually modify that?
So the resummation we did is in momentum space. So it's not directly affecting the moments because the moments are mostly encoded in the short distance factorization, in the short distance correlations. And in principle, the momentum space resummation is not exactly equivalent to the to your resummation in short distance. They are not equivalent. But or in other words, they are resumming different logarithms at a higher order, not exactly the same. And if you want to examine the effect of moments, the math itself could not tell you about that because it is a factorization that's only in momentum space. It cannot extend to the full range of x. But for moments, you always need an integral over all x region.
All right. Thank you.
You need a short distance factorization that helps you understand the moments.
Okay, so another question. There have been some results from like MSU and Temple on the GPD calculation, right?
Yeah.
You actually do check their result using your resummation?
Yeah, we do plan to coordinate with one of them, their groups, to apply the method to real lattice data.
Okay.
Yeah, but so far, I think the results they have at hand correspond to rather small Kasai region. So they don't have a very large Kasai. Like in my test, I use 0.5, but they clearly
Okay.
don't have this large Kasai. So in principle, if you have like Kasai only equals 0.1 or zero point 0.2, you may get a very small ERBR region that, yeah, probably you can extract useful information there, but we can test the DGLAP region. Yeah.
That's right. Okay. Okay. Thank you.
Mhm.
Maybe I can ask a question. In your large log, there's no scale. For the GPD, there's no scale like z times pz, right? So the calculation itself should be smooth as z equals 0.
We are matching in momentum space, so there is no parameter of z here.
Sorry, I mean x.
X times bz. Oh, yeah, there's not supposed to be any logarithm at x equals 0 because this actually corresponds to x equals 1/2 here in DA.
Yeah, but
It's a
I
different
do
function.
remember that they are lattice calculations. Their result is not continuous at x equals 0. Is that?
That's probably because they are working in the zero skewness limit.
It's a
Yeah,
non-zero skewness. I think it's skewness equal to 1/3.
I do remember they have discontinued. They have some issue at Kasai that's not smooth, but probably not at 0. I can check that. Thank you. Yeah. So which please like maybe, yeah, I will check it. But I don't think there would be any issue at x here for non-zero skewness. It's not appearing in the matching kernel at least, even to higher orders. So maybe one possible issue could be that numerical Fourier transformation. If their numerical Fourier transformation suggests that the x equals to 0 largely depends on the long range correlation function, then in principle, you can get some issues at x equals 0. Probably due to just the Fourier transformation.
Yes, thanks.
Thank you.
Any other questions? Yeah, now let's thank the speaker again.
Thank you. Thank you for attending.